Okay, so we're doing question number 18, and in this problem we're given a charge Q1 of 5 coulombs at 345. So this is question number 18, and we have a charge Q1, and it's 5 coulombs. It's located at 3, 4, and 5 in space, and we're told that there's another charge Q2. Oh no, actually find the potential difference between 2 points in space. So we're given 2 points. A is a point, it's located at 1, 2, 3, and B is a point located at 3, 2, 1. Am I recording? Yeah. So, and we have to find the potential difference from VA and VB. So we have to find the absolute potential, and then we have to find the difference between the potential. So we're actually calculating the difference, VBA, which is B minus VA. That's what we're trying to have to calculate. So get a rough idea what's happening. So we're going to calculate the absolute potential at each of the points relative to this. So let's calculate VA. The potential at VA is going to be K. Actually, before I do that, I should draw a little diagram to make sure you're understanding. So we should always do a little diagram to make sure we understand what's happening. So somewhere in space we have a charge Q, Q1. So here's the charge. And we have 2 points in space, so relative to some coordinate system. So here is, let's call this position vector RQ. Then we have a point in space called A, and let's call this position vector RA. And then we have another position vector called RB. Actually, it looks too vertical. So let's just put it this way over here somewhere. So RB. So here's our y-axis, and here's your x-axis, and this is a z-axis. Okay. So RA, RB, RQ. So we're trying to find the absolute potential difference of these 2 points. It's the electric potential difference between VA and VB. So how do I get, so really I'm trying to find the distance from these 2 points. And so this vector drawn from 2Q to A is the vector QA. And the vector drawn from Q to B is RQB. Okay, so let's calculate first RA. The position vector for RA is given by, how do we get to there? From the origin you have to travel 1 meter in the I direction, 2 meters in the J direction, 3 meters in the K direction. So this is position vector for A is going to be 1I plus 2J plus 3K. And the position vector for B, how do you get from the origin to that position? That's the position vector. It's going to be 3 meters, because we're using standard units, right, which are going to be our natural units for calculations are going to be. That's why I don't put any units anywhere. It's going to be kilogram meter and second, and volts and ampere and whatever. So it's 3I plus 2J plus 1K. And the position vector for the charge itself is going to be 3I. Is it 3I? Yeah, it's 3I plus 4J plus 5K. Okay, so remember, we're trying to understand the ideas, not to confuse you with numbers and stuff. Okay, so these are nice, easy, round numbers. So I have to find the position vector of Q1 R, the vector drawn from Q to A, RQA. So this would be equal to RA, the position vector A, minus the position vector RQ. So in this case it happens to be, RA happens to be 1I plus 2J plus 3K minus RQ is 3I plus 4J plus 5K. So 1 minus 3, which is negative 2I. 2 minus 4 is negative 2j. 3 minus 5 is negative 2k. So that's our position vector QA. Let's repeat the process for our QB, the vector drawn from Q to B. So that would be RB vector. Sorry, oops. Mistakes abound. RB minus the position vector of RQ. And I'll actually stay in one line because I'm running out of space and I don't want to erase things. RB and RQ. RB happens to be, is there enough space on the board? Yeah, I think so. RB is 3i. Actually, you know what? I will put on the next line just in case. Okay, so this is R3i plus 2j plus 1k minus RQ, which is 3i plus 4j plus 5k. So 3 minus 3i, which is 0i, 2 minus 4, which is negative 2j, 1 minus 5 is negative 4. Okay, so we have the position vectors. So how do I calculate the potential at VA? And I need to put some space somewhere, but let me summarize these two results because these are the only two vectors I really need. So I'll summarize everything that we need. So the vector drawn from Q to A, we calculated it to be minus 2i minus 2j minus 2k. The position vector from Q to B is equal to 0i minus 2j minus 4k. Okay, so I'm going to erase everything else. We don't need anything else, so let's calculate the potential for VA. So we're actually calculating the absolute potential. So the absolute potential is actually relative to the infinity. So we're actually saying that far away from the particle at infinity, really it's an infinite sphere, far away the potential is at 0. It's relative to that point. The potential at VA is going to be the potential generated by Q1, which in this case happens to be, where is Q? VA. Potential is going to be K Q1 over the magnitude of RQA. Okay. So this is the absolute potential at this point. And then we'll calculate the absolute potential at B and then take the difference to get the correct answer. So VA is going to be KQ1. So it's 9 times, it's actually 9. Remember, all my significant digits, I only doing it up to 2 significant digits because we are trying to understand the problem, not waste time in calculations. So this is really 9.0 times 10 to the 9. So I'm always doing 2 significant digits only. Q1 happens to be a charge of 5 coulombs. And the distance, the magnitude of RQA, which is, so remember, RQA is the magnitude of the vector. So I'll just write, just make sure you understand. This is an abbreviation for the magnitude of RQA. Magnitude. So this is really nothing more than the square root of minus 2 squared plus minus 2 squared plus minus 2 squared. You can see it from there. This is the component. And then VB is equal to KQ1, the same charge, but now the position vector is QB, the distance to QB. Sorry, not the position vector, the distance from Q to B. So that's equal to 9.0 times 10 to the 9 times the Coulomb charge of Q1. Q1 is 5 coulombs, right? Same number. And the distance to that is 0 squared plus minus 2 squared plus minus 4 squared. And so we'll get back numbers. So I won't bring up the calculator and do this, but so the final answer is VA minus VB. The potential difference between those 2 points is going to be these two difference between these two numbers, 9.0 times. I'll actually write it out just to make sure you're understanding, because I'm not going to plug this into a calculator. And really, on an exam, I expect you to write these equations down because I'm testing you on your understanding of concepts. I'm not testing your understanding and how fast you can like plug in a calculation into a calculator. It's really important that you understand to build the idea. The idea is more important than these calculations. So the second equation is this. So if I had to, I can plug into a calculator, but really the idea that so my exams are testing you on your understanding concepts. Okay, so and what is the answer in? Well, potential is going to be in volts. So the answer, whatever number it is going to be the answer in volts. And remember, this is I'm writing out explicitly the units instead of using a symbol because some of the symbols become like they look like variables, and I don't want you to get confused. Okay, so this is question number 18.